Once we have a molecular orbital diagram, we can find out some properties of the molecule. We can calculate bond order by taking the number of electrons in bonding molecular orbitals and subtracting the number of electrons in antibonding orbitals, then dividing by 2. In the molecular orbital diagram for hydrogen, we can see that 2 electrons are in the sigma bonding molecular orbital, which doesn't contain a star, and 0 electrons are in the sigma star antibonding molecular orbital. 2 minus 0 divided by 2 equals 1. The bond order for hydrogen is 1, which corresponds to a single bond. This makes sense based on the Lewis structure of the hydrogen molecule. We can calculate the bond order for a helium-2 molecule. It would have 2 electrons in a sigma bonding molecular orbital and 2 electrons in a sigma star antibonding molecular orbital. 2 minus 2 divided by 2 equals 0. The He2 molecule would have a bond order of 0, meaning no bond forms. This molecule does not exist in nature. A bond order of 1 would be a single bond, a bond order of 2 would be a double bond, and a bond order of 3 would be a triple bond. However, there can also be non-integer values of bond order. Having more electrons in bonding molecular orbitals makes a bond more stable and more likely to form. Having more electrons in antibonding molecular orbitals makes a bond less stable and less likely to form. When we calculate bond order, it is okay to ignore the core electrons. Because they essentially cancel each other out, like in the helium molecule, they don't add or take away from the bond order. As effective nuclear charge increases and radius decreases across a row, the orbital energies go down. It goes down dramatically in some molecular orbitals, such as sigma 2px, but much less dramatically in other orbitals, such as pi 2py and pi 2pz. Because of that, the relative energies end up switching partway across the periodic table. In lithium through nitrogen, the sigma is higher than the pi's. In oxygen through neon, the pi's are higher than the sigma. Because the order of the energies is a bit tricky, I will generally give you the blank molecular orbital diagrams, and you will just need to fill in the electrons. Rather than drawing out the molecular orbital diagrams for all the elements in the second row of the periodic table, we can write electron configurations, which are much more compact and give almost the same information. See if you can turn these electron configurations into molecular orbital diagrams. For example, the electron configuration for the dilithium molecule tells us that there are 2 electrons in a sigma 2s molecular orbital. It has 2 bonding electrons and 0 antibonding electrons, so 2 minus 0 divided by 2 gives a bond order of 1. The diberyllium molecule has 2 electrons in a sigma bonding molecular orbital and 2 electrons in a sigma star antibonding molecular orbital. 2 minus 2 divided by 2 gives a bond order of 0. After this, we start to see a pattern of the bond order going up by 1 for each element. That is because each element has 2 more electrons in bonding molecular orbitals. After dinitrogen, the bond orders start going down by 1 because each molecule has 2 more electrons going into antibonding molecular orbitals. Eventually, we get to neon, which has equal numbers of electrons in bonding and antibonding, so it has a bond order of 0. The molecular orbital diagram for oxygen explains why it is paramagnetic. When we fill in the molecular orbital diagram, we follow the Aufbau principle and Hund's rule. The last 2 electrons to be filled in go into separate pi star antibonding molecular orbitals. Because the molecule contains at least 1 unpaired electron, it is paramagnetic. For practice, fill in the provided molecular orbital diagram for the beryllium-2 -2 ion and predict the bond order and whether it is paramagnetic or not. Please consult the poll question key to see an image of the filled-in molecular orbital diagram. Each beryllium starts with 2 valence electrons. but there are also 2 extra electrons because of the -2 charge. I would put 1 extra electron into each beryllium. Total, there should be 6 valence electrons filled into the center of our diagram containing the molecular orbitals. 2 come from each beryllium, plus the last 2 from the -2 charge. When we fill the electrons in, we follow the Aufbau principle and Hund's rule. So 2 electrons go into the sigma 2s, 2 electrons go into the sigma star 2s, and the last 2 electrons go into separate pi orbitals. To calculate bond order, we take the bonding electrons and subtract the anti-bonding electrons, then divide by 2. The electrons in the sigma 2s and the pi orbitals are bonding, since there is no star next to the name of the orbital. That means there are 4 bonding electrons. The electrons in the sigma star 2s orbital are antibonding, so there are 2 antibonding electrons. 4 minus 2 divided by 2 gives a bond order of 1. Finally, this molecule would be paramagnetic because of the unpaired electrons in the pi molecular orbitals. Molecular orbital theory differs from valence bond and hybrid orbital theory in some key ways. In valence bond and hybridization theory, electrons in bonds are located between just one pair of atoms. In molecular orbital theory, all of the electrons are delocalized throughout the whole molecule. In valence bond theory and hybridization, bonds are formed by overlap of atomic orbitals. With molecular orbital theory, instead of overlapping orbitals, the atomic orbitals are combined together to make completely new molecular orbitals. In valence bond and hybridization theory, bonds can be either sigma or pi. In molecular orbital theory, there is still sigma and pi, but those sigma and pi can be either bonding or antibonding. With valence bond theory and hybridization, the shape is determined by the number of electron domains. Molecular orbital theory is better equipped to predict the arrangement of electrons in molecules. With valence bond theory and hybridization, multiple resonance structures are needed to describe delocalization of bonds. Molecular orbital theory has one unified structure.